LLM token, context window.
Oh yeah, RH prompt function calling.
Right, exactly. MCP agent, skill. If you have been, anywhere near the internet or a corporate boardroom or literally any tech blog in the last couple of years, you are just completely drowning in this alphabet soup.
It is everywhere.
It really is. You click a button, a paragraph of code appears, or like a perfectly written email gets drafted. And under the hood, it feels like absolute magic.
Or maybe more accurately, it feels incredibly murky.
Yeah, murky is the perfect word for it. It's just this avalanche of buzzwords that keeps coming. Every single week, there is a new fancy term to learn.
It is incredibly overwhelming. And frankly, the tech industry doesn't do you or anyone else any favors by constantly inventing new, highly polished packaging for what are essentially the exact same underlying concept.
Right.
It creates this illusion that you need a PhD in computer science just to understand what's happening on your own screen.
Exactly. And, that is exactly why we're here today. Welcome to the Deep Dive.
So glad to be here.
If you are listening to this right now, you are the learner. You are the person who wants to cut through the noise, who is tired of the information overload, and who just wants to understand how the machine actually works.
That is the goal.
And I am about to drop something on you that completely blew my mind when we were going through all the research and documentation for this deep dive. Are you ready for the core, surprising revelation?
I think we just need to lay it out there.
They are all the same thing.
Yes, they really are.
Every single one of those buzzwords I just rattled off. LLMs, agents, skills, function calling. They are all just different angles, different layers of the exact same underlying mechanism.
And that is the overarching mission of our deep dive today. We are going to completely demystify what developers call the AI stack.
The AI stack.
Right. We're going to build it for you right here, layer by layer. We'll start from the absolute bedrock and work our way all the way up to these, autonomous agents everyone is terrified of.
Okay, I love that.
But to do that, to clear up those murky waters, we have to establish the foundational, indisputable rule of the technology we are looking at.
Okay, let's establish the ground rules. What is the absolute bedrock truth here?
The rule is this. A large language model, an LLM, can only do one thing. It outputs text.
Wait, that's it?
That is it.
Okay, let's unpack this because I'm going to push back immediately. That statement feels like it contradicts literally everything I see when I open up one of these applications. You're telling me it just outputs text.
Yes. It cannot browse the web. It cannot query your company's database.
Right.
It cannot open a spreadsheet. It can't control your mouse. It can do absolutely nothing except produce a string of characters.
But hold on. If it can only output text, how is it writing and executing Python code for me? How does it check the real-time weather in Tokyo?
Well, that's the thing.
Like, how does it act as an agent that goes out, searches the internet, reads 3 different articles, and summarizes them? Because I have watched it do these things with my own eyes.
That is the illusion. You have watched the system do those things. The LLM itself cannot do any of them.
What do you mean?
The human-written program surrounding the LLM does all of that.
Wait, the program surrounding it?
Yes. And this brings us to the guiding metaphor for our entire conversation today. It's a phrase you are going to hear over and over again until it is burned into your brain.
Okay, let's hear.
LLM talks, program walks.
LLM talks, program walks.
Precisely. The program, the actual app or interface you were using reads the text that the LML outputs.
You see.
It takes action in the real world on behalf of that text, and then it feeds the result of that action back to the LLM. That is the whole trick.
So the LLM is just talking.
Exactly. The LLM is essentially a brain trapped in a box, doing nothing but speaking. The program provides the hands, the feet, and the sensory organs outside the box.
That is a massive paradigm shift. It completely flips the dynamic.
It really does.
And I promise you, the listener, by the time we are done with this deep dive, you are going to possess a mental model that will allow you to see through any future AI buzzword.
Absolutely.
No matter how fancy the marketing gets, you will be able to trace it back to this simple reality. So if we are building this stack from scratch, we have to start at the bottom, right? The brain and the box.
Right. The word prediction engine.
The LLMs and the tokens.
If we want to understand the system, we have to understand its atoms. And at its core, a large language model is not a thinking machine.
It's not thinking at all.
No, it is purely a word prediction machine. We really need to strip away the anthropomorphism here.
The human traits we project onto it, right?
Exactly. When you type a complicated question into a chat interface and it types back a beautifully formatted essay, You feel like you are talking to a very smart, very well-read intern.
Oh, totally. It feels like a person.
But mathematically, you are interacting with a highly complex autocomplete function. It's basically your phone's keyboard autocomplete, just scaled up to a monstrous size.
I was reading through the notes on this, and there was a really great, simple example that just made the mechanics click for me. Let's walk through it.
Let's do it.
So imagine you, the user, type the phrase, "The capital of France is."
Okay, so you feed that phrase into the model. The model looks at the sequence, the capital of France is.
Right.
And its underlying mathematical function calculates the most statistically likely next word based on billions of pages of text it has seen before.
Okay.
In this case, it predicts the word Paris.
Boom! Paris. Simple enough, but it doesn't just stop there and wait for me to clap.
No, because it's a loop.
Yeah.
It takes that newly predicted word, Paris, it appends it to your original input, and it feeds that whole new string back into itself.
Oh, wow.
So literally a millisecond later, the new input it sees is, the capital of France is Paris.
And then it has to predict the next piece.
Exactly. Now it looks at that whole sentence and calculates the next statistical likelihood. Maybe it predicts a comma. So it appends the comma. The capital of France is Paris, comma. Then it feeds that back in. Then it predicts the word which. Then the word is.
Just over and over.
Yes. And on it goes, looping and predicting, looping and predicting.
But how does it know when to shut up? Because sometimes it gives me 2 sentences and sometimes it gives me 5 paragraphs.
It loops until the mathematical function decides the sequence is probabilistically complete. At that point, it outputs a very specific, invisible piece of data.
Invisible.
Yeah, it's called a stop token.
A stop token. Literally a signal that says, I'm done predicting now, cut the mic.
Yes. And the philosophical takeaway here is absolutely crucial for the learner to internalize. There's no thinking happening in that loop.
Not at all.
There's no understanding of what the concept of a capital actually is. There's no consciousness, no reasoning, no concept of European geography.
Right, it doesn't know what France is.
Exactly. It is just doing one thing. Given the text so far, what is the most mathematically probable next sequence of characters?
But wait, here is a catch that completely threw me when I first learned it. We keep saying it predicts words.
Right.
But the model's internals, like the actual engine doing this predicting, is made of pure matrix math.
Yes, it is.
It's just massive arrays of numbers, weights, and parameters multiplying against each other.
Yeah.
It doesn't actually understand text at all. It only understands numbers.
That's right. A computer processor cannot multiply the word France by a matrix of weights. You can't do math on the letter F.
Yeah, that makes sense.
You need numbers. So how do we bridge that gap? If you type in English and the model only speaks math, we need a translator.
And this translator sits right between me and the mathematical engine.
Exactly. And this translator is called the tokenizer.
The tokenizer. Okay, this is a word that gets thrown around constantly. People talk about token limits and cost per token.
Oh, all the time.
But seeing how it actually works is wild.
The tokenizer has a very specific two-way job. On the way in, when you type your message, the tokenizer chops your text up into small chunks. These chunks are the tokens. It then takes a massive dictionary it has and maps each of those text chunks to a specific, unique ID number.
So it turns letters into numbers.
Yes. Those numbers are what actually get fed into the matrix math of the model.
And then the reverse happens on the way out, right?
Yeah.
The model does its massive algebraic equations and it spits out a sequence of numbers.
Yes. The tokenizer catches those numbers, looks them up in its dictionary, converts them back into readable text chunks, and pastes them onto your screen.
But here's where my brain kind of broke,
Yeah.
and it's the really counterintuitive part about tokens.
Okay, what is it?
We think of language in terms of human grammar. We think of syllables or whole words. But a token is not a word.
No, it is not. And this trips up almost everyone who starts building with these tools.
The tokenizer doesn't care about human grammar. Let's look at a specific example. Take the word helpful.
Okay, helpful.
If you type that, the tokenizer splits it into 2 tokens. It splits it into help and full.
Now, that one makes logical sense to us. It looks like a root word and a suffix. We can map that to our understanding of English.
Right.
But it's not doing that because it took a middle school grammar class.
Right, because look at another example. The word unbelievable. The tokenizer splits that into 3 distinct tokens.
What are they?
It splits it into unbelieve and able.
Unbelieve and able. 3
Yeah.
different numbers representing those 3 chunks.
Why does it split them that way? Why not split unbelievable into 4 chunks? Why not just treat it as one giant chunk?
What's fascinating here is the underlying logic. The splitting pattern isn't based on a dictionary or linguistic rules.
Then what is it based on?
It is based purely on statistical patterns the model learned during its massive training phase. The tokenizer essentially scanned the vast ocean of text on the internet and learned which combinations of letters appeared together most frequently.
Ah, so un appears together a lot. Able appears together a lot.
Exactly. Yeah. Un, believe, and able are highly frequent letter groupings across millions of documents.
Yeah.
So the engineers optimized the translation process around those frequent chunks.
It's basically a shortcut.
It is a compression technique. It's much more efficient for the computer to process common chunks than to process every single letter individually, or to try and memorize every single distinct word in existence.
So it doesn't know what a word is. It only knows statistical chunks.
Yes. And if we connect this to the bigger picture, this is exactly why LLMs historically struggle with tasks that seem incredibly simple to a child.
Oh, like what?
Have you ever asked an LLM to count how many R's are in the word strawberry? Or asked it to spell a word backward?
Yes. It fails miserably. It will confidently tell you there are 2 R's in strawberry.
Exactly.
And it makes you think, how can this thing write a Python script but fail at counting letters?
It fails because the brain inside the box never sees the letters. It only sees the numbers representing the chunk.
Oh.
If strawberry is tokenized as one single chunk, the model just sees one ID number. It literally cannot see the R's inside it. You are asking it to analyze the letters of a word it has never actually looked at.
That is profound. So the key takeaway for you listening right now is this. Tokens are the literal atoms of the AI world.
They really are.
They are the fundamental building blocks of everything that happens. Everything goes into the model as tokens, and everything comes out of the model as tokens.
You can think of the whole system as a very advanced, incredibly fast game of word chain, played exclusively with these atomic numbered chunks.
Okay, so we've built the brain. We have an LLM that is an absolute genius at playing this token chain game. It can predict the next chunk flawlessly.
Yes, it can.
But there is a fatal flaw in this design, a massive glaring limitation if we want this thing to actually be useful.
A structural amnesia.
Yes, the LLM has absolute zero memory.
None. Zero.
But wait, if I talk to an AI for an hour, asking follow-up questions, refining my prompts, it remembers what I said 20 minutes ago.
It seems like it does.
Right. If I ask it to tell me a joke, and it does, and then I type, explain why that's funny, it knows exactly what that refers to. How is that possible if it has no memory?
This is where we move from the brain to the architecture surrounding it. The concept of context and the illusion of memory.
The illusion.
Yes, because the lack of memory isn't just a metaphor, it is literal.
So the math function just terminates.
Exactly. Input goes in, tokens come out, and the math function powers down. It clears its RAM completely.
Oh.
The next time you hit enter, the model knows absolutely nothing about you, the previous call, or the joke it just told you. It has the memory of a goldfish. Actually, worse. It exists entirely in the present millisecond.
So what is the trick? How is the program faking it so well?
The trick is what developers call the stitched history. Every single time you type a new message and hit enter, the program running behind the scenes, the chat interface on your screen, quietly gathers up your entire conversation history from that session.
The whole thing.
The whole thing. It stitches the whole thing together into one massive block of text, appends your new question at the very bottom, and sends the entire bundle to the LLM all at once.
Every single time.
Every single time. The LLM does not just look at your new question. It reads the full conversation from the very first hello you typed an hour ago, all the way down to the punchline of the joke, and finally your new question.
That is insane.
It hasn't remembered anything. It is literally rereading the entire transcript from scratch every single time you hit enter.
Okay, let's unpack this. That is astonishingly inefficient. If I've been talking to it for 3 hours, it's rereading a novel's worth of text just to answer my next sentence.
Yes, it is pure computational brute force.
Yeah.
And this entire bundle of information, basically everything the LM is allowed to see and read at any given moment, is known by another massive buzzword.
Let me guess.
Context.
Context. Okay, you got it.
So context is just everything it sees. Context includes everything. It's your current question, the stitched chat history, hidden system instructions we'll talk about later, a list of available tools. It is all crammed in together into one giant text block that gets fed to the tokenizer.
I love the analogy used to explain this. We have this idea of the context window, and the best way to visualize it is as a physical desk.
The desk metaphor is perfect because it introduces physical constraints.
Right. Imagine the LLM is an office worker sitting at a desk. The desk represents the context window, and that desk has a strict physical size limit.
You can only fit so much on it.
Exactly. You can only fit so much paper or so many tokens on the desk before it starts falling off the edges onto the floor.
And if a piece of paper falls off the edge of the desk, the LLM cannot see it. It is gone.
Out of sight, out of mind.
Yep. And if it cannot see it, it cannot use that information to predict the next word.
Which explains why in the early days of this tech, if you had a really long conversation, the AI would suddenly forget your name or what you talked about at the beginning.
Right. The paper fell off the desk.
The earliest parts of the conversation were literally being pushed off the edge of the desk to make room for the new messages.
Exactly. The context window was too small. But let's talk about the scale of things today because it has exploded. The leading models right now have a context window, a desk size of roughly 1 million tokens, sometimes even 2 million.
Okay, 1 million tokens. What does that actually mean? Let's translate those atoms back into human terms for the listener.
1 million tokens is roughly 750,000 English words.
750,000 words. To frame that scale, that is the equivalent of taking all 7 Harry Potter books. All of them.
That's a lot of pages.
Piling them onto the desk at once and having the LLM read every single page from scratch in a matter of seconds, just to answer your one question about what spell Harry used in Chapter 4 of Book 3.
It is a massive, massive desk.
Okay, so if the desk is that big now, here's my question. Why not just use that brute force for absolutely everything?
What do you mean?
Let's say I'm a mechanic, and I have a massive 1,000-page, highly technical PDF product manual for a Boeing airplane. Why not just dump the entire 1,000-page manual onto the desk every single time I ask the AI a question about a loose screw?
What's fascinating here is that while the desk can hold it, practical engineering limitations make that a terrible idea.
Really? Why?
First, there is speed. Even for a supercomputer, tokenizing and processing 1 million tokens takes time. You'd be waiting 20 seconds for every reply.
Oh.
Second, there is the cost. You are paying the AI company for compute power per token. Dumping a 1,000-page manual into the context window for every single question will run up a massive server bill almost instantly.
And beyond speed and cost, there's a third reason, right? It actually makes the AI dumber.
Yes, the lost-in-the-middle phenomenon. If you put 1,000 pages of text on the desk just to find one paragraph about a specific screw, the LLM gets completely overwhelmed by the sheer volume of irrelevant noise.
It just gets buried.
Exactly. Its attention mechanism gets diluted. It might hallucinate an answer or pull information from the wrong chapter because it's trying to process a mountain of garbage data to find one gem.
So we have a cluttered desk problem. We want it to know about the airplane manual, but we can't give it the whole airplane manual. What is the solution?
The solution is perhaps the biggest enterprise buzzword of the last year: RAG.
RAG, R-A-G, Retrieval Augmented Generation.
It sounds incredibly intimidating and academic.
It sounds like a military protocol or something.
It really does. But when we break it down plainly, it is an incredibly simple concept. RAG simply means don't dump everything on the desk, pick what matters.
Okay, explain the mechanics of how that actually works, because the LLM doesn't know what matters until it reads it, right?
Right. So we use a separate system. Think of RAG as a librarian who works in the office with the LLM.
Okay, a librarian.
Instead of dumping the 1,000-page manual on the LLM's desk, you give the manual to the AI librarian. The librarian files it away in a special database. Now, you ask your question. What is the torque specification for the left wing screw?
The librarian hears the question first.
Exactly. The RAG system, which is a separate, much cheaper, much faster search program, scans the manual ahead of time.
Oh, before the LLM even sees it?
Yes. It looks for keywords or semantic meaning related to torque, left wing, and screw. It finds the 3 specific pages in the manual that mention those things.
And then?
It pulls those 3 pages out and puts only those 3 pages on the LLM's desk.
Oh, okay, the acronym just clicked perfectly for me.
Let's hear it.
You retrieve the relevant information from the database. You augment the context window, the desk, with those 3 pages. And then the LLM generates the answer. Retrieval augmented generation.
You keep the desk clean.
Yeah.
You only give the LLM the exact hyper-relevant context it needs to predict the right words.
But wait, what happens if the RA librarian messes up? What if the search program pulls 3 pages about the landing gear instead of the wing?
Then the LLM will confidently give you the wrong answer. Because remember, the LLM is just predicting words based on what is on the desk.
It trusts the librarian.
Completely.
Yeah.
If you put garbage on the desk, the LLM will predict garbage. It doesn't know the librarian made a mistake. It assumes whatever is in its context window is the absolute truth.
Which is exactly why fixing hallucinations usually isn't about fixing the LLM itself. It's about fixing the RG system so it grabs the right pages.
Precisely. You have to train a better librarian.
Okay, so let's check our progress on building this stack. We've got the tokenizer chopping our text into mathematical atoms.
Yep.
We've got the LLM engine playing the prediction game. We've got the context window desk holding our stitched chat history so it has a fake memory.
Right.
And we have our RAG acting as the librarian, putting relevant reference material on the desk. The LLM has its workspace completely organized.
But we are missing the spark.
Right. How do we actually tell it what to do? If I just open a chat box and say, hello, how does it know whether it should respond like a friendly customer service rep, a pirate, or a terse Python coder? Where does its personality come from?
That brings us to the next layer of the stack, prompts.
Yes. Prompts. Let me just pause here and address you, the listener, directly. The word prompt gets so overly mystified.
Oh, heavily mystified.
You hear terms like prompt engineering, prompt mastery, or prompt wizardry. People on LinkedIn make it sound like you need to learn ancient spellcasting to talk to an AI.
It has become a very lucrative cottage industry, but the reality is much more grounded.
A prompt is just what you say to the LLM. It is the text you give it. That's it. It's instructions.
However, there is a nuance here that is critical for understanding the stack. There is a dual prompt system at play that most casual users don't realize.
A dual prompt system?
Yeah. When you're using an AI app, there are actually 2 distinct kinds of prompts operating simultaneously on that desk.
Let's break those down.
The first is the user prompt. This is the obvious one. It's what you, the user, literally type into the chat box.
Like, write me a sorting algorithm in Python.
Or give me a recipe for chicken soup.
Mm.
Summarize this email. The user prompt sets the immediate task. It dictates what needs to be done right now.
Simple enough. I am the user. I prompt the machine. But what's the second kind? Because I only ever see one text box.
The second is the system prompt, and this is the invisible puppeteer.
Ooh, I like that.
These are the hidden rules set by the developer behind the scenes. The user never sees them, but they are absolutely vital for the AI to function in a predictable way.
Give me a real-world example of what a system prompt looks like. What is actually written in there?
If you're using a coding assistant, the developer might write a system prompt that says, you are a senior Python engineer with 20 years of experience.
Okay.
Keep all your answers concise and professional. Always add detailed inline comments to your code. Do not use informal language or emojis. Under no circumstances should you write code in JavaScript.
So every single time I ask it to write code, the LLM is reading that hidden paragraph before it reads my actual request.
Every single time.
Mm-hmm.
The program packs that system prompt onto the desk in the context window right at the top before it adds the chat history or your user prompt.
So if the user prompt establishes what needs to be done, the system prompt establishes who the AI is pretending to be and what its unbreakable rules are. It creates the baseline persona.
Without a system prompt, the LLM is just a chaotic autocomplete. It might drift into weird tangents or adopt strange tones. The system prompt acts as the guardrails.
Okay, let me summarize where we are because this is the absolute turning point of the deep dive. The LLM can predict words. It can see its stitched history in the desk.
Right.
It can read the reference pages the REdge librarian gave it. And it can follow the script laid out by the user and system prompts. It is fully prepped.
It is fully prepped to talk.
Here's where it gets really interesting. Because despite all of this context, all of these instructions, and all of this math, it is still just outputting text.
Just text.
We still haven't solved the core mystery I brought up at the very beginning. How does text become an action in the real world? How does a sequence of tokens book a flight?
This is the crux of the illusion, the most critical mechanism in modern AI, the concept of function calling.
Listener, if you are doing the dishes right now, or driving, or walking the dog, pull your focus in. Let the dishes sit for 5 minutes.
Yeah, this is the big one.
If you remember only one thing from this entire discussion, let it be this exact mechanism. This is the secret to the magic trick. This is how the brain in the box reaches out and touches the real world.
We must reiterate the fundamental fact one more time, just to be crystal clear. The LLM cannot check the weather.
Right.
It cannot read your local files. It cannot call an API. It has no internet connection of its own. The program around it does it.
So how does the weather actually get checked? Let's meticulously walk through the exact step-by-step flow. We are going to slow this way down, like an instant replay in a sports game.
Okay, I'm ready.
The scenario is simple. I type into the chat interface, what is the weather in Tokyo?
Okay, this is a 10-step process.
Yeah.
Step 1, you type the question, what's the weather in Tokyo?
Yeah.
Now, note carefully, you are asking the program, the chat interface, not the LLM directly.
Right. I hit enter on my keyboard. The app catches my text.
Step 2, the program springs into action. It assembles the context desk. It takes your question, it grabs the hidden system prompt, it grabs the stitched chat history, and crucially, it grabs a list of tools that the program is allowed to use.
Tools? Oh.
It bundles all this onto the desk.
Okay, so the program puts a piece of paper on the desk that says, hey, LLM, just so you know, I have a tool called GetWeather that requires a city name.
Exactly. Step 3, the program sends this entire context desk to the LLM.
Okay, the brain sees the desk.
Now, step 4. This is a critical moment. The LLM starts its token prediction engine. It analyzes all that context. It sees you want the weather. It sees there's a weather tool available on the desk.
Right.
And because it has been heavily trained to recognize this exact situation, it realizes it shouldn't just guess the weather. It needs to ask the program to use the tool.
So what does it output? Because it can only output text.
It outputs a very specific piece of highly structured text. It outputs a JSON format.
Wait, let me interject. JSON. JavaScript object notation. It sounds technical, but conceptually, what is it?
Think of JSON as a standardized, incredibly rigid, fill-in-the-blank form. Computers use it to talk to each other without misunderstanding.
Like a structured document.
Yeah, instead of writing a messy paragraph like, hey, program, could you please check the weather for Tokyo? The LLM outputs a form that says, tool name equals getWeather. Argument equals Tokyo.
Full stop. Let's freeze the replay right here.
Yeah.
The LLM just produced a string of text that looks like a filled-out form.
That's all it did.
The LLM's job is completely done here. Its math function powers down. It did not reach out to a server in Japan. It did not check a thermometer. It just predicted that a JSON form requesting the Tokyo weather was the statistically correct response to my prompt.
That is the dividing line between the brain and the hands. The LLM is finished. Now we move to step 5.
Okay, what's step 5?
The program, the actual software running on your computer or in the cloud, reads that piece of JSON text the LLM just spat out. It parses it. It reads the form.
It interprets it.
Exactly. It realizes, oh, the LLM wants me to use the GetWeather tool, and it wants me to check Tokyo.
Step 6, the program itself, using traditional non-AL computer code, sends a web request out to an external weather API on the internet.
Step 7, the external weather API does the actual work. It checks its database and returns a raw data result back to the program. Let's say it returns cloudy, 18 degrees Celsius.
Step 8, the program catches that data. It packs it into a brand new piece of paper, puts it back on the context desk, and sends the whole desk back to the LLM again.
Step 9, the LLM wakes up again. It reads the new desk. It sees your original question, what's the weather in Tokyo? It sees the JSON form it previously filled out.
And it sees the new data.
Yes. And now it sees a new piece of paper from the program that says system observation, cloudy, 18 degrees. Based on all of that context, it runs its prediction engine one last time.
And it outputs words.
Yes. Outputting a human-readable sentence. It is currently cloudy in Tokyo and roughly 18 degrees Celsius.
And finally, step 10. The program takes that beautifully formatted human-readable sentence and displays it on your screen.
Let's synthesize what just happened.
Yeah.
In step 4, the LLM output a structured text form. In step 9, it output an English sentence.
2 pieces of text.
2 pieces of text.
Yeah.
That was all it did. The surrounding program did all the assembling, the parsing, the actual internet API calling, the relaying, and the formatting.
LLM talks. Program walks.
There it is in action.
The LLM talks. It outputs a text request form. The program walks. It goes out to the internet, gets the data, and brings it back.
Exactly.
The LLM is entirely paralyzed. It cannot take a single step on its own. It just passes notes to the program, and the program runs the errands.
Every advanced concept that follows in this deep dive,
Yeah.
the agents, the skills, the complex orchestration frameworks, they are built entirely on this specific loop.
It's all just this loop.
It is. The architecture might get more complicated, there might be more tools, but this foundational loop, talk, walk, feed it back, never ever changes.
That clears up so much the murky water. When I see an AI doing something in the real world, I now know it's just passing a note to a normal piece of software.
It's just a note passer.
But exploring this raises another question. If the program has to do the walking, if the program has to actually call the external tools, how does a program know what tools are available in the first place?
This brings us to a massive bottleneck that developers faced and the solution that just revolutionized the space.
What's the solution?
The concept of MCP, the USB-C of AI.
Okay, let's pose a hypothetical to the listener to explain the problem. Imagine you are a brand new employee at a massive legacy corporation.
Okay, I'm picturing it.
There are dozens of internal software systems. There's an HR portal, a ticketing system, a sales database, an expense tracker. But on your first day, nobody gives you a directory. Nobody tells you what the tools are, how to log in, or what data they require to work.
You would be completely lost. You couldn't do your job. You don't even know what you don't know.
Exactly. And the program running the LLM faces the exact same problem. If we wanted to check the weather, read a GitHub repository, or search our private company Notion database, the program needs to know those tools exist.
Right.
It needs to know their exact names, what parameters they require in that JSON form, and what format the data will come back in.
This is where MCP enters the picture. MCP stands for Model Context Protocol. It sounds highly academic, but its job is incredibly practical.
What does it actually do?
It is a small, standalone program that acts as that missing tool directory.
Okay, so how does it work?
An MCP server has two primary functions. First, the catalog. When your AI program boots up, it essentially taps the MCP server on the shoulder and asks, "What tools do you have?"
Like asking for a menu.
Exactly. The MCP server returns a full, comprehensive list. It says, I have a weather tool, and here is the exact JSON form required to use it. I have a file reading tool, and it requires a file path. It provides the complete instruction manual for every available action.
And the program takes that catalog and puts it on the LLM's desk in the context window, so the LLM knows what it is allowed to ask for.
Exactly. Then comes the second function, execution. When the LLM outputs that JSON text saying, use the weather tool, the program hands that request over to the MCP server.
So the MCP server takes over.
Yes, the MCP server is the one that actually runs the code, hits the API, and returns the result to the program.
So it's a dedicated middleman for tools, a universal translator for actions.
It is.
Okay, let's unpack why this is so revolutionary, because we need to understand the dark ages before MCP existed. Let's talk about the pain developers were in.
It was a lot of pain.
Let's say I spent months building an amazing complex tool that allowed an AI to securely query my company's financial database. I would have to write hundreds of lines of custom bespoke code to connect that tool to ChatGPT's specific API format.
Yes, you would.
Then, 3 months later, Claude releases a better model. I want to use Claude now. But Claude's API expects the tools to be formatted slightly differently, so I have to rewrite all the connection logic from scratch.
And then?
Then Google's Gemini comes out. I have to rewrite it again.
You were building the exact same tool 3 different times because every AI platform spoke a slightly different language for function calling. It was a fragmented nightmare.
And the brilliant analogy for how MCP solves this is the USB-C cable.
It's the perfect way to visualize it. We all remember having a drawer full of different charging cables.
Yeah.
You had a micro USB for your headphones, a mini USB for an old camera, a proprietary connector for your phone.
I still have that drawer.
We all do. You never had the right cable when you needed it. Then USB-C became the global standard. One cable works for everything. Your laptop, your phone, your headphones.
Build once, run everywhere. If you build your financial database tool as an MCP server, it acts as a USB-C port.
Exactly.
It can instantly be plugged into any AI program that supports the standard, whether that's ChatGPT, Claude, or a local model running on your laptop. You just plug in the MCP cable, and the program instantly has access to the catalog and the execution capabilities.
So let's summarize our progress again. We have a single talks and walks loop. The LLM outputs text forms, the program executes them.
Right.
And now with MCP, we have a unified standardized tool catalog, so the program easily knows exactly what actions are possible across any model.
It's elegant, but real-world problems are rarely solved in just one single step, right?
No, they are not. Life is complicated.
Checking the weather is one round trip. LLM talks once, program walks once, gives the data, done. But what happens when the task gets complicated? What if the goal requires adapting to new information halfway through?
This leads us into the next layer, the autonomous loop. And this brings us face to face with the buzzword everyone is obsessed with right now, the thing that has CEOs terrified and excited, agents.
Yes. Agents. Agentic AI. You hear this everywhere. Let's move beyond the single round trip. Give me a scenario of a complex problem that requires an agent.
Okay, let's build on our weather example, but make it messy. Instead of just asking for the weather, imagine the user types. What is the weather where I am right now? And if it is raining, find me a nearby umbrella shop.
Okay, that is not a single function call. That's a multi-step logic puzzle. It has a conditional statement, if it is raining, and it requires chaining different tools together.
Exactly. Let's break down the chain reaction of what happens under the hood when an agent tackles this. Step 1, the LLM reads the prompt. It realizes it cannot check the weather because it doesn't know where you are.
Oh, right.
So it talks. It outputs a JSON form requesting the get location tool.
Good.
The program walks, executes the tool, and returns your GPS coordinates to the context desk.
Step 2. The LLM reads the desk. It sees the coordinates. Now it can check the weather. It talks, again, outputting a second JSON form for the get weather tool, passing in those specific coordinates.
Exactly.
The program walks, checks the weather API, and returns the data to the desk. The data says, it is currently raining.
Step 3, the LLM reads that it is raining. It remembers the original instruction, if raining, find an umbrella shop. The condition is met.
So it moves to the next action.
Yes, so it talks a third time. It outputs a JSON form for a search maps tool, looking for umbrella shops near the coordinates it found in step 1. The program walks, executes the map search, and returns a log of 3 shops to the desk.
And finally, step 4. The LLM sees the list of shops. It realizes it has fulfilled all parts of the user's prompt. It combines all of this gathered information on the desk and outputs the final human-readable answer. It is currently raining at your location. Here are 3 umbrella shops nearby.
This multi-step process, where the system can plan the sequence of actions, execute them one by one, observe the results, and continuously loop until the overall overarching condition is met. That is the definition of an agent.
Wait, let me stop you. So an agent isn't a new kind of super smart LLM. It's not a secret GPT-5 running in a bunker.
No. And this is the biggest misconception in the industry. The LLM inside an agent is the exact same word-predicting brain we talked about in step 1.
Are you serious?
Yes. An agent is just the surrounding architecture. It is the talks and walks loop put on an autonomous repeat. Talk, walk, feedback. Plan the next step. Talk, walk, feedback. It loops until the task is complete.
That's it.
That's it. This is exactly what tools like Claude Code or Cursor or GitHub Copilot are doing under the hood when they build a whole website for you. They are just running this multi-step loop over and over.
If we connect this to the bigger picture, there is a mind-bending truth here that shifted how I view these systems completely.
Yes, the zero intelligence insight.
Explain that, because it radically demystifies the fear around autonomous AI.
Let's look at the actual physical actions taken in that umbrella scenario. Getting a GPS location from a device, checking a weather API, searching Google Maps for a store.
Okay.
The program did all of those things. And crucially, doing those things requires zero intelligence. It is just deterministic computer code running basic, rigid API calls.
A basic script written in 1995 could do those specific actions.
Exactly. The program acting on the world is entirely blind and mechanical, just runs the code it's handed. The LLM's only job in that entire sequence was acting as the central planner. It analyzed the context and decided which dumb mechanical action to take next.
So an intelligent agent, this futuristic concept we're also hyped about, is actually assembled almost entirely from parts that possess no intelligence whatsoever.
Pretty much.
The LLM just sits in the very center, blind and paralyzed, acting as the decision engine. It says, run this script, and the dumb mechanical program goes and runs it.
That is the reality of the AI stack. The intelligence, the reasoning, is entirely contained in the planning and the text generation. The agency, the actual impact on the world, is entirely mechanical and human-coded.
Okay, so the agent can plan on its own, it can loop, it can use tools, but here's my pushback.
Was here.
Let's say I want this agent to help me at my job. I want it to be my coding assistant. The agent doesn't intuitively know my specific company rules or my team's quirky standard operating procedures or my personal preferences.
No, it doesn't.
How do we give it those rules so it plans correctly? If it just plans based on general internet knowledge, it's going to mess up my company's specific workflow.
That is the final piece of the puzzle. The top of the stack how we guide the agent's autonomy. And this introduces our final buzzword, skills.
Let's ground this with a scenario for the listener. You are a software engineer, and your team has a very strict, highly specific deployment checklist.
Very common.
Before you push code to production, you must pass all unit tests, you must verify the environment variables in a specific secure folder, you must confirm a rollback plan in case things break, and you must ping the on-call engineer on Slack.
A standard, rigid procedure that every new hire has to memorize.
Right. Now, you want your new fancy AI agent to handle this deployment for you, but you absolutely do not want to sit there and type out that massive 50-step checklist into the chat box every single time you deploy. That defeats the whole purpose of automation. You'd spend more time prompting than coding.
You need a way to preload those rules. You need to give the agent a handbook.
So what exactly is a skill? When I hear a company say, our agent has a deployment skill, what does that actually mean under the hood?
It sounds like they downloaded a martial arts program into its brain, like in The Matrix.
I know Kung Fu.
Exactly. But the reality is almost comedically mundane. A skill is just those rules, written down in a document and stored in a fixed location for the agent to consult whenever it needs to. It is literally just a markdown text file.
Just a text file.
A basic text file with a title, a description, and step-by-step instructions.
Let's be honest here. A skill is literally just a prompt that lives in a different folder and has a fancier name.
Essentially, yes. It is pre-written context. It is old wine in a new, highly marketed bottle.
But looking closely at how agents use these files, there is one genuinely clever aspect to how skills are designed. It's not just dumping text. It's a concept called progressive disclosure.
This is critical. And we have to go back to the desk metaphor, the context window, to understand why it's necessary.
Right. The desk has limited space.
Exactly. If your company has 500 different skills, a markdown file for deployments, one for HR onboarding, one for expense reporting, one for writing marketing copy, you cannot dump all 500 files onto the LLM's desk at once.
It would crush the desk.
It'll exceed the token limit, it will cost a fortune in compute, and the LLM will get completely lost in the noise, just like the 1,000-page manual.
So how does progressive disclosure solve this? How does the agent know what rules to follow without reading all of them?
Think of it like a researcher in a massive library. Level 1. When the agent first boots up, it doesn't read the books. It only scans the titles and a one-sentence description of all the available skills.
Okay.
It's like glancing at the card catalog. Okay, there's a file about deployments, a file about HR, a file about expenses, very low token cost. Just a few pieces of paper on the desk.
Okay, so it has a high-level map.
Right. Now, level 2. You tell the agent, hey, help me deploy this code. The agent looks at its map and realizes, the deployment file matches this task. Only then does it actually pull that specific file off the shelf and load the full instructions onto its desk. It opens the relevant book.
And level 3, because sometimes a checklist references other documents.
Level 3 is depth. If those deployment instructions contain references to other documents like Step 4, check the server configuration file located in folder X, those secondary documents are only retrieved and loaded onto the desk if the agent specifically reaches that step and needs them.
Like checking a footnote.
It's exactly like reading a book, seeing a footnote, and only flipping to the bibliography if you actually need to verify the source.
Let's do a deep analysis of this, because why build it this way? We've touched on it, but the trade-off here is the defining constraint of building AI applications.
It is the ultimate trade-off between token cost and information completeness. In the AI world, tokens equal money and tokens equal time.
So efficiency is everything.
You want to give the LLM just enough information to succeed at the current step, and not one token more. Progressive disclosure ensures the agent isn't overwhelmed by noise, and you, the developer, aren't running up a massive cloud computing bill loading irrelevant data. It is a highly optimized, dynamic way of feeding prompts to the brain exactly when it needs them.
Wow, okay. We have reached the top of the stack. We've gone from the microscopic math to the autonomous loop. Let's move into our outro and do a full stack synthesis. I want the listener to picture this in their mind.
It is so helpful to zoom out and look at this entire AI world we've built today, layer by layer, from the bottom up.
Listener, visualize this stack. At the very foundation, you have the absolute truth. The LLM outputs text. It predicts atomic tokens based on matrix math. That is its only capability.
Above that, you have the context window, the desk, which holds the memory faked by the stitched chat history.
You have RBREG acting as the librarian, picking only the relevant information to put on the desk so the LLM doesn't get distracted.
You have prompts both the user's instructions and the hidden system instructions, which provide the rules and the persona.
Then you hit the bridge to the real world, function calling. This is where text turns to action. The LLM outputs a JSON text form, and the program walks. It executes the external command.
Above that, MCP acts as the universal catalog, providing the standard directory of tools so the program knows exactly what it can plug into, like a USB-C cable.
Then the agent layer. This takes the talks and walks loop and puts on autonomous repeat, allowing it to plan, execute, and adapt to solve complex multi-step problems.
And finally, at the very top, you have skills. Pre-written markdown files that provide the standard operating procedures, loaded dynamically via progressive disclosure so the agent knows exactly how to navigate your specific company rules.
That is the stack. That is the magic trick laid bare.
Yeah.
And I want to reiterate the core thesis of this entire deep dive one more time, because it is so easy to forget when you're using these tools. None of these capabilities, the web rising, the memory, the tool usage, the multi-step planning, none of them belong to the LLM itself.
They are all illusions created by the surrounding human-coded architecture. The LLM's sole isolated contribution to this entire marvel of modern technology is simply outputting the right sequence of text characters at the right time.
So we promised the listener an ultimate mental model, a tool they can carry with them to navigate the murky waters of AI buzzwords forever.
Yes, we want to empower you. The AI industry is going to keep inventing new words.
They definitely will.
The next time you are sitting in a meeting or reading a tech blog, and someone tried to sell you on a brand new revolutionary concept, maybe they call it multi-agent orchestration architecture or agentic RAG flow or whatever the next buzzword is, do not be intimidated. Do not assume it's magic. You only need to ask 2 clarifying questions to cut entirely through the noise.
Question 1, what specific text did the LLM output?
And question 2, who read that text and what program turned it into an actual action?
I completely agree. Answering those 2 questions makes any opaque, overly marketed tech concept instantly transparent. If you can identify the text the brain predicted, and you can identify the code doing the walking, you understand exactly how the system works. It demystifies the magic completely.
It grounds the technology in reality.
It really does. But before we wrap up, I know you have a final provocative thought for the listener, something for them to mull over as they leave this deep dive and go back to using these tools.
I do.
Yeah.
If we connect everything we've talked about today to the broader conversation happening in the world, there is a lot of existential fear right now about AI.
Yeah, a lot of it.
People worry about AI waking up, or developing its own secret motivations, or autonomously taking over critical systems. We picture the sci-fi Terminator scenarios.
Right. The rogue AI.
But if you truly internalize the mechanical stack we discussed today, if you fundamentally understand that all an AI does is sit in a box and predict a string of text tokens, and that it is the surrounding human-written program that actually grants it power, agency, and access to the real world,
Right.
this raises a very important question. When we worry about AI going rogue and causing harm, should we really be staring in fear at the language model predicting words? Or should we be looking much, much closer at the careless, highly permissioned programs we humans are writing to walk on its behalf?
Oh, man. That is a chilling thought. The monster isn't the brain in the jar, it's the mechanical suit we keep deciding to plug it into. The landscape isn't murky because the AI is inscrutable. It's murky because we keep building more and more complex machinery around the word predictor.
Exactly.
Thank you for that incredible synthesis, and thank you, the listener, for taking this deep dive with us. Keep asking those 2 questions and stay curious out there.